Okay, so we are now continuing section 10.2, derivatives and integrals of vector functions. So let me give you a moment to copy this example down. All right, so let's see here. We want to, in this case, we want to find parametric equations for the tangent line to the curve that has these parametric equations. And you might wonder, what is this, what does this space curve look like? What is the space curve, what does space curve C look like? Well, we're going to see what that looks like in a little bit here. But first of all right, when you're encountered with one of these kind of problems, it's helpful, I find it very helpful to draw a picture. So what do we have here? We have a space curve C, given by these three parametric equations. Space curve is traced out in space, and at some point, the space curve is going to pass through the point √3, 1, and 2. So, of course, we have to ask ourselves, for what value of t would that be? For what value of t would that be? And that really requires us to know some trigonometry. So, okay, I would focus on, the cosine of what angle t equals √3, and the sine of what angle t equals 1. What angle, what angle does t have to be? That's right, Narina. It has to be 30 degrees, or pi over 6. The sine of, because, well, if we think of it like this, So in order to get, let's take the y component. Y component is 1, right? So that means the sine of t would have to equal 1/2. Well, when t is pi over 6, or let me rephrase it here. Yeah, when t is pi over 6 or 30 degrees, the sine of pi over 6 is equal to a half. So put that over here, equals 1/2. So, and by the way, the cosine of t, cosine of t, well, the x component is √3, so the cosine of t has to be √3 over 2, right? √3 over 2. Well, the cosine of pi over 6, which is right, 30 degrees, that also equals √3 over 2. So t is pi over 6. So let's draw a little sketch. Here's a little sketch of the situation. Okay, so let me just add a little bit to the picture. Get this font down a little bit. Okay, so here is my position vector, r of t, okay, coming from the origin. And when t is pi over 6, we arrive at the point with coordinates √3, 1, and 2. That's this point right here. We want the tangent vector. We want to know, okay, what is r prime of pi over 6? So we have to find derivatives of these components for r of t. Remember what r of t was. I'll write it down here just so we have it. Just add a little detail here. Right, 0, 0, 0, that's the origin. And by the way, get that out there, r of t was 2 cosine of t times 2 cosine of t, comma, 2 sine of t, and then 4 cosine of 2t, right? So using chain rule a little bit here to get our components up for our derivative vector. And now we're going to evaluate the derivative vector at pi over 6.
Wait, I'm sorry. Why is z multiplied by 2?
Why is z multiplied by 2? Oh, that's the chain rule. That's the chain rule. Or so the derivative of the cosine of 2t is, let me just write this a little more. I mean, I think it's okay, but let me just write it a little bit here. I'll write it out, okay? So what's the derivative of the cosine? Negative sine. Negative sine. Okay, yep, that's right. But then you got the 2t here, derivative of 2t is 2. So this here is by the chain rule, Aura,
Okay, now I see. Thank you.
You're welcome. And so we end up with these, we end up with this derivative vector, and now we put in pi over 6 everywhere. Now web assign wants simplified radical form answers, not decimals. So all right, the sine of 30 degrees is a half. Cosine of 30 degrees is root 3 over 2. And so the derivative vector r at pi over 6 is has these components: -1 root 3 and -4 root 3. So now what we're looking for, right, is I can add this to the picture, I guess. I don't know if it'll work. Let me see here. Actually, hold on. Let me just add a little bit more to this picture here. I just like to put my space curve in red. And there's the derivative vector in black. And I'd like to draw a line through that. So maybe the line, I'll put that in this color here. So hopefully, well, that's not any good. Hold on. That's not going to work. Hold on. What I'm trying to do is I'm trying to find a line segment feature that but I can't do it like this. I'll be here for, well, all right. Tell you what, I'm just going to draw the line. I'm not going to, let me just draw it. Oh, hey, I think I discovered. All right, there we go. There's the line. See? That's the line I'm looking for. I dashed it for you. The line, that line in orange passes, it's parallel to the vector r prime of pi over 6, and it passes through the point root 3, 1, 2. The point with coordinates root 3, 1, and 2. And so here are the parametric equations for the tangent line. There they are. Now, wouldn't it be nice? Wouldn't it be nice? Well, are there any questions? Yes, Alberto. So just we got pi over 6. Well, the sine, so like just take the middle, hold on here. So let's see here, hold on. So take the 1 here, right? So 2 times the sine of what angle? is going to equal 1. Well, the sine of the angle has to be a half, so the sine of 30 degrees is pi over 6. See that? With your 30, 60, 90 right triangle. Okay, you're good. All right, good, good. All right, are there any other good questions? Okay, Alexander's good. All right, now, good. So, all right, we have these parametric equations of the tangent line, but of course it would be nice if we could verify those parametric equations. Could we graphically do a check, an illustration? The answer is yes. The answer is yes. We can take the parametric equations, okay, and of our tangent line, we can take those parametric equations, and we can take I want to kind of have things, we can take the parametric equations of the space curve, and I actually wrote some code in MATLAB that will graph both the position vector r prime of t and the tangent line to the space curve at when t equals pi over 6. Let me show you. Let me show you. So here, whoops, here is the code. And if you look in Blackboard under MATLAB programs, this code is shared code now. Okay, if you look in, if you would look, how many are, if you click on the MATLAB programs link in the menu, the tab, there should be a section 10.2 program you can click on. When you click on it, does it bring this up? All right, Yeva says it works. Good, good. Okay, so you know we're gonna graphically verify this result. So what's going on here with the code? Well, first of all, we need to have the I don't know why it does that. First of all, with the code, we need to define our symbolic variable using the sims t command. And once again, I think probably everybody now has installed MATLAB, most all of you. But remember, when you install MATLAB, be sure to include symbolic toolbox because it's not part of the standard installation. And if you installed MATLAB with standard installation, you can go back in and just add the symbolic toolbox, add it, you know, and get that installed. Okay, so the first plot here, I'm using what's called the fplot3 command because I want to plot a space curve in three-dimensional space. This is r of t. Okay, and then I use what's called the hold on. The hold on. I'm telling MATLAB, hold on. I'm not done yet. I want to add another curve to my picture. Well, that curve is the tangent line. So the tangent line is given here. Hold on one moment. No, yeah, these are the parametric equations for the tangent line. And I just choose to let t go from negative pi over 3 to 2 pi over 3. I'm just going to graph, I'm not, you know, obviously a line goes on forever. So I'm going to restrict the value of t to go from, say, negative pi over 3 to 2 pi over 3. And incidentally, for the space curve for r of t, I restricted t to go from 0 to 2 pi because the trig functions have periods of 2 pi or less. Okay, so that's how that works. And let me just see here, one moment. Right, so then if you put this in MATLAB, you should get a picture like something like this, where it draws this interesting space curve. You notice the space curve, it's not a helix, it's a self-contained curve because all the components are trig functions that are cyclical. If the curve, just as t increases, it just retraces itself again. And then there's the tangent line at the point x equals √3, which is about 1.7, y equals 1, and z equals 2. Now, let me just show you in MATLAB here real quick. Let me just bring it up in MATLAB. Yeah, it looks like a Pringle. That's right, Ivy. It kind of looks like a Pringle. Let me just bring it up in my last minute or two here. Let me just bring up the MATLAB. So definitely that line is tangent to the space curve. No question about that. If we go into the MATLAB, here it is. Here's the code, and I'm going to copy the code and paste it in the command line and hit enter. And hopefully it'll graph this. It does graph it. It does graph it. And hopefully, if you're trying it, it's graphing it for you. If we, let me just go back in here one moment, back to the window. How many are getting a figure like this? How many are getting a figure? Hold on. Okay, Yeva sees that. And excellent. And by the way, if you go to the figure and if you click on view, well, hold on, where is it? Oh, tools. You can rotate the figure. You can rotate it. Okay. I mean, you can do a lot of things. See? You can rotate and change your orientation, whatever you want. How many think that's pretty cool? Yeah, I'm liking it too. I'm liking it too. All right. Well, so that is then, I think with these examples, you ought to be able to manage the section. That's okay, Simon. You ought to be able to manage the section 10.2 homework that's due on Thursday. We'll get into integrals in our next class. Are there any questions before I stop the recording?
Professor?
Okay, yeah, it was good. Yes, Alexander.
Can I meet with you after class?
Yeah. Actually, let me go ahead and stop the recording here. No problem. Very good. All right, if we're good here, one moment. Excellent.